The river of time might not always flow forward. We are about to explore a concept that could shatter your understanding of reality, the physics of temporal eddies. By the end of this, you will see the universe as a place where the past, present, and future might not be so clearly separated. We will uncover how Einstein's equations allow for time to loop back on itself, and what strange signatures these cosmic whirlpools could leave behind. How would your life change if you knew the path behind you was not fixed? Our daily lives are built upon a simple, undeniable truth: time moves forward. You cannot unburn a log, unspill a glass of milk, or unlive a single moment. This one-way street is what physicists call the arrow of time. It is the reason we remember the past and anticipate the future, never the other way around. This relentless forward march is most famously described by the second law of thermodynamics, which states that entropy, a measure of disorder, always increases in an isolated system. A tidy room will inevitably become messy, a hot cup of coffee will cool to room temperature, and a scrambled egg will never spontaneously reassemble in its shell. Yet here lies the profound mystery: the fundamental laws of physics, the very equations that govern particles and forces, do not care about this direction. If you were to watch a film of two electrons repelling each other, and then watch that film run in reverse, you would see a sequence that is also perfectly valid according to the laws of electromagnetism. At the smallest scales, the universe appears ambivalent about past and future. So where does our powerful, universal experience of a one-way flow come from? The answer seems to be written in the history of the cosmos itself. The most compelling candidate for the source of time's arrow is the cosmological arrow, the fact that our universe is expanding from a singular, incredibly ordered state we call the Big Bang. That initial state of low entropy set the stage for everything that followed, creating a gradient down which disorder could steadily increase. Our psychological arrow of time, our personal stream of consciousness, is likely a consequence of riding this thermodynamic wave. But if the arrow's existence depends on the unique conditions of our cosmic environment, a fascinating question arises. Could there be places in the universe where those conditions are different, where the river of time does not flow in a straight line, but instead curls back on itself? To find those temporal eddies, we must first understand the fabric they twist. The rigid, universal clock of Newtonian physics was forever dismantled by a single mind. Albert Einstein revealed that time is not a fixed backdrop against which the universe plays out, but a dynamic, flexible dimension intimately woven with the three dimensions of space into a single fabric called spacetime. This was the core of his theory of special relativity, which introduced a startling truth: the faster you move through space, the slower your clock ticks relative to a stationary observer. This time dilation is not a mechanical error. It is a fundamental property of the universe, verified by countless experiments with ultra-precise atomic clocks on fast-moving jets and satellites. But Einstein did not stop there. His general theory of relativity painted an even more dramatic picture. It proposed that mass and energy tell spacetime how to curve, and that curved spacetime tells matter how to move. This is what we experience as gravity. A planet like Earth does not pull on you with an invisible force. Instead, its mass creates a depression in the cosmic fabric, a gravity well, and you are simply following the curved path within that well. This warping has a direct effect on time itself. At the bottom of a deep gravitational well, like the surface of a dense neutron star, time passes noticeably slower than out in the empty void of space. Your feet being ever so slightly closer to Earth's center of mass actually age slower than your head, a tiny but real effect measured with sensitive instruments. This profound flexibility is the key. If the fabric of spacetime can be stretched and dimpled by mass, could it, under the most extreme conditions, be twisted into a loop or knotted into a structure that reverses its local flow? The mathematical equations Einstein gave us, the very foundation of general relativity, do not explicitly prohibit such bizarre geometries. They leave the door wide open for solutions where the paths through spacetime could curve so severely that they turn back on themselves, creating the theoretical possibility of temporal eddies. Understanding this malleable nature of reality is the essential first step toward believing that the river of time might not have a single, unwavering current. This theoretical possibility for backwards time travel brings us directly to one of the most fascinating structures in all of physics, the wormhole. Often called an Einstein-Rosen bridge, a wormhole is not a bridge through space, but a tunnel through the very fabric of spacetime itself. Picture the universe as a vast, flat sheet of paper. If you wanted to get from a dot on one side to a dot on the other, the normal route would be a long line across the surface. But if you could fold the paper, bringing those two dots together, a wormhole would be a pencil punching straight through the fold, creating an instant shortcut. These cosmic tunnels are not just shortcuts through space, they are potential gateways through time. The mechanism hinges on the time dilation we just explored. Imagine you have a wormhole with two mouths, an entrance and an exit. You keep one mouth, mouth A, stationary here on Earth. The other mouth, mouth B, is placed on a spaceship that travels out into the cosmos at a significant fraction of the speed of light. Because of time dilation, time for the moving mouth B will pass more slowly. After a year of travel from the perspective of Earth and mouth A, the ship returns. Only 6 months have passed for mouth B. Here is the incredible consequence. The wormhole has permanently connected these two different points in time. If you were to jump into the stationary mouth on Earth, you would instantly emerge from the moving mouth B, but you would emerge at the time registered by that mouth. You would travel back to a point 6 months before you even jumped in. You would have traveled backwards in time. This creates what physicists call a closed timelike curve, a path through the cosmos that loops back on itself. This is the precise definition of a temporal eddy, a whirlpool in the river of time where the current flows in a circle. Now, the monumental catch is that holding such a tunnel open requires something truly bizarre, exotic matter. This is not antimatter, but a hypothetical substance that possesses negative energy density, effectively generating a form of anti-gravity that pushes the tunnel walls apart, preventing the wormhole from instantly collapsing into a singularity. While we have never observed such matter in bulk, the fact that wormholes are valid solutions to Einstein's equations of general relativity means the universe does not mathematically forbid them. Their theoretical existence provides a stunningly clear blueprint for how a region of backwards flowing time could be engineered, or might even exist naturally, hidden in the deepest folds of the cosmos. But if wormholes are cosmic shortcuts, black holes are the universe's ultimate dead ends, or so we once thought. These gravitational monsters represent the most extreme warping of spacetime imaginable. Their immense mass, often millions of times that of our Sun, is crushed into a point of infinite density known as a singularity. Here, at the very heart of a black hole, the fabric of reality is torn apart, and our current understanding of physics simply breaks down. You cannot reach this point, however, without crossing the event horizon, the famous point of no return. Once matter or light passes this boundary, it is lost to our universe forever. Yet the space just outside this horizon is a maelstrom of activity, especially around a rotating black hole. This region is called the ergosphere, and here, space-time itself is not just curved, it is dragged. The black hole's immense spin pulls the very fabric of the cosmos around with it, like a spinning ball submerged in a thick, cosmic fluid. This phenomenon, known as frame dragging, twists the environment into a turbulent whirl. It is within these incredibly bizarre conditions, near a singularity, that some physicists speculate the arrow of time might not just slow down but could potentially reverse. Certain solutions to Einstein's equations, particularly those describing rotating black holes known as Kerr black holes, suggest their interiors could be even stranger than their exteriors. The mathematics hint that inside a rotating black hole, the paths an object must take could curl into closed time-like curves. An astronaut unfortunate enough to survive the plunge might find themselves on a trajectory that does not lead to a crushing end, but instead loops back to an earlier moment, trapped in a repeating cycle of their own past. From our perspective, safely outside, we would witness another profound temporal distortion. As an object falls toward the event horizon, the intense gravitational field causes such severe time dilation that its clock appears to tick slower and slower. To our eyes, the object would seem to freeze, its image reddening and fading, as it takes an infinite amount of our time to ever actually cross the horizon. It is a place where time, from an external view, grinds to a halt. Black holes are not merely destructive voids, they are the universe's most extreme natural laboratories, testing the very limits of how time can behave. Yet for all its power, general relativity is not the final word on how our universe operates. It masterfully describes the cosmos on its largest scales, the graceful dance of galaxies and the crushing curves around black holes. But to find the true, fundamental nature of time, we must shrink our perspective down to the subatomic realm, to the bizarre and counterintuitive world of quantum mechanics. Here, the rules are completely different, and time itself becomes a far more slippery concept. In the quantum world, particles do not have definite states or locations until they are measured. An electron can exist in a state of superposition, meaning it is in multiple places or spinning in multiple directions at once. This foundational weirdness directly challenges our everyday understanding of cause and effect. How can you say one event causes another when the events themselves are not even definite until they are observed? This leads to profound questions about the sequence of time. Some interpretations of quantum mechanics, like the Wheeler-Feynman absorber theory, propose that the theory is fundamentally time-symmetric. In this view, the equations work just as well if time runs backwards. A particle emitted from one point and absorbed at another could be described as a single, seamless process where the distinction between cause and effect melts away. From this perspective, the absorption of the particle in the future could be just as responsible for its emission in the past as the other way around. This is the radical idea of retrocausality, where future events can probabilistically influence the past. While it remains a highly debated concept, it forces physicists to reconsider the unbreakable chain of causality we take for granted. These quantum ambiguities are thought to be most extreme in the vacuum of space itself. Empty space is not truly empty. At the unimaginably tiny Planck scale, space-time is believed to be a seething, turbulent foam. Here, pairs of virtual particles and their antiparticles constantly pop into existence, borrowing energy from the vacuum for a fleeting moment before annihilating each other and vanishing. In this chaotic, frothing sea, the very ideas of before and after may lose all meaning. The orderly progression of time we experience in our macroscopic world could be an emergent property, a calm average that arises from this underlying quantum chaos. The temporal eddies we have been exploring, the great whirlpools in the river of time, might not begin with massive black holes or wormholes. They could have their origins right here in the probabilistic, uncertain, and deeply strange quantum foundation of reality itself. If time is a river, its current may be born from the turbulent rain of the quantum foam. This is the mathematical heart of a temporal eddy, a closed time-like curve. Picture a single path through the cosmos, the world line of a particle or a person. In our normal experience, this line moves inexorably forward through time, never doubling back. But within a closed time-like curve, that path does something extraordinary. It loops. It bends so severely through the warped fabric of space-time that it returns to its own starting point, not just in location but in time. You could, in theory, follow this path and meet your former self. This is not science fiction, but a direct and startling prediction that falls out of Albert Einstein's own equations for general relativity. The brilliant logician Kurt Gödel first discovered these loops while exploring solutions for a universe that was rotating as a whole. His work proved that the math of our best theory of gravity does not forbid a universe where time itself is circular. A closed time-like curve is the purest expression of a backwards flowing river, a self-contained whirlpool where the current of time spins in a perfect, unbreakable circle. The immediate and terrifying question this raises is the famous grandfather paradox. What if you were to travel back along such a curve and prevent your own grandfather from meeting your grandmother? The logical inconsistency is glaring. You would never be born, therefore you could never travel back to prevent the event, meaning you would be born after all. It is a catastrophic rupture in the chain of cause and effect. Yet some physicists like Igor Novikov argue the universe would not allow it. They propose a self-consistency principle, a cosmic rule that any actions taken within a closed time-like curve must be consistent with the history that already exists. You could travel to the past, but you would be physically prevented from creating a paradox. Your gun would jam, your foot would slip, some seemingly random event would conspire to ensure the timeline remains intact. In this view, free will within the loop becomes an illusion. Your journey to the past was always a part of that past, and your actions there were predetermined to ensure the stable reality you left behind. This forces us to confront the very bedrock of our existence. Is the future open and malleable, or is it, like the past, already written? If closed time-like curves exist even on a microscopic scale, they would create pockets of reality where, from our perspective, time runs in reverse. Particles would appear to experience effects before their causes, and the very meaning of before and after would lose its anchor. The river does not just flow backwards in these eddies, it flows in a perfect and perhaps inescapable ring. But we do not need to venture into a black hole to find a potential whirlpool in time. Another, more subtle cosmic structure could twist the fabric of reality, one born from the very first moments of creation. In the intense heat of the early universe, as it expanded and cooled, the fundamental forces may have undergone sudden shifts, much like water freezing into ice. And just as ice can form with cracks and fissures, these cosmic phase transitions could have left behind defects, flaws frozen into the fabric of spacetime. The most fascinating of these are cosmic strings, hypothetical filaments thinner than a proton but possessing unimaginable density. A single inch of cosmic string could weigh more than a mountain range. These are not strings of matter, but true topological defects, cracks in reality itself. Their gravitational influence is bizarre. Space around a cosmic string is not flat but conical. Imagine taking a flat sheet of paper and cutting out a thin pizza slice, then taping the edges back together. The surface still looks flat locally, but a global path around the tip of that missing slice would bring you back to your starting point having traveled less than 360 degrees. This is the geometry around a cosmic string. It creates a gravitational lens that can produce double images of distant galaxies, but its most incredible property involves motion. If two such strings were to whip past each other at a significant fraction of the speed of light, the spacetime between them would become so twisted that a path could form a closed time-like curve. A spacecraft could fly a precise loop around these moving cosmic strings and, from our perspective, arrive back at its starting point before it ever left. Even a single string, if it were tied into a loop, could theoretically create a stable time machine within its center. The profound implication is that temporal eddies might not be confined to the violent hearts of black holes. They could exist as large-scale architectural features of the cosmos, woven into its structure from the beginning. These cosmic cracks are not powered by immense singularities, but by the pure, strange geometry of the universe itself. While we have no confirmed observations of these strings, their theoretical possibility shows us that the potential for time loops could be written into the very blueprint of reality, waiting in the vast voids between galaxies. The key to unlocking a stable gateway through time may lie in a substance that defies common sense, exotic matter. This is not the antimatter of science fiction, but something far more bizarre. While normal matter possesses positive energy density and creates the attractive gravity we are familiar with, exotic matter would flip this script. It would have a negative energy density, and in the equations of general relativity, this produces a repulsive gravitational effect, a form of anti-gravity. Picture trying to hold open the mouth of a wormhole. The immense gravitational pull of the structure would naturally want to crush it shut in an instant, snapping the tunnel closed. Exotic matter would act as a kind of cosmic strut, its repulsive gravity pushing outward against the collapsing walls, keeping the throat of the wormhole permanently propped open. Without this theoretical substance, any attempt to create a traversable bridge through spacetime would fail catastrophically. The most astounding part is that the seeds of this strange material might already exist within the fabric of our reality, hinted at by a well-known quantum phenomenon. In a perfect vacuum, empty space is not truly empty. It is a seething sea of virtual particles that constantly flicker in and out of existence. If you place two perfectly smooth, uncharged metal plates extremely close together in this vacuum, something remarkable happens. The plates exclude some of the longer wavelength virtual particles from the space between them. This creates a region of lower energy density between the plates compared to the higher energy density outside. The result is a measurable force that pushes the plates together. This is the Casimir effect, and the region between the plates is effectively a zone of negative energy density. It is a laboratory demonstration that the laws of quantum mechanics do permit the existence of the very exotic matter required to stabilize a wormhole. The catch, of course, is scale. The Casimir effect produces only a minuscule amount of negative energy. To prop open a wormhole large enough for even a single particle to pass through would require astronomical quantities, perhaps the negative energy equivalent of an entire star, concentrated and controlled. This immense challenge makes the idea of engineering a temporal eddy seem nearly impossible. Yet the principle stands firm: the universe does not forbid negative energy. If nature, under conditions we do not yet understand, can somehow concentrate this exotic substance, then stable wormholes and the closed time-like curves they create could be woven into the cosmos, not as science fiction, but as features of its deepest physical laws. Even the ultimate speed limit of the cosmos, the speed of light, might have a loophole. tachyons are a purely hypothetical class of particles born from the mathematics of special relativity itself. They are defined by one astonishing property: they always travel faster than light. According to Einstein's theory, as an object with real mass approaches the speed of light, the energy required to accelerate it further approaches infinity. This is the cosmic speed limit we all know. Tachyons, however, would sidestep this entirely by starting their existence already beyond that barrier. They would never slow down to the speed of light, only faster. This bizarre nature leads to even stranger consequences. For a tachyon, mass is not a real number. The equations demand it be an imaginary number, a mathematical concept involving the square root of -1. While this sounds like science fiction, it is a direct, if unsettling, output of our most trusted physical laws. The most profound implication, however, involves time. In the framework of relativity, a tachyon's experience of time would be inverted relative to our own. From our perspective, a tachyon moving faster than light would be traveling backwards in time. If we could somehow track one, we would see its effect occur before its cause. Imagine a tachyon message being received before it was ever sent, a clear violation of the logical sequence we depend on. This is why most physicists are deeply skeptical of their existence, as it would shatter our understanding of causality. Yet the theoretical possibility remains a tantalizing thought experiment. It suggests that the river of time might have multiple simultaneous currents. We are trapped in the slow, forward-flowing water, but other entities could be surfing a backwards-flowing wave we cannot perceive. If tachyons are real, they would not need to find a temporal eddy. They would be living proof that such eddies are a fundamental part of the cosmic fabric. They would be natural inhabitants of the reversed time regions we have been searching for, a permanent part of the universe's hidden undercurrent. This idea of a predetermined loop brings us directly to one of the most compelling solutions to the grandfather paradox. Proposed by the physicist Igor Novikov, the self-consistency principle is a bold conjecture about how reality might protect itself. It asserts that the past is not a fragile script that can be rewritten, but a robust, finished story. If you were to enter a closed time-like curve and travel to the past, your actions there were always a part of that history. You cannot change what has already happened because you were always there, a participant in the events that unfolded. Your free will within the loop becomes an illusion, constrained by the absolute requirement that you do nothing to create a logical inconsistency. Imagine traveling back to prevent a famous historical fire. You might arrive with the best intentions, only to accidentally knock over a lantern with your own foot, becoming the very cause of the disaster you hoped to stop. Your presence did not alter the timeline, it completed it. This principle acts as a potential physical law, a cosmic editor that governs temporal eddies. It ensures that within these whirlpools where time flows backwards, the river's current, however twisted, never truly contradicts itself. Cause and effect remain sacred, even when the effect appears to happen before the cause from our linear perspective. This transforms the concept of time travel from a chaotic paradox generator into a complex, predetermined dance. Every movement is choreographed in advance to ensure the final, consistent picture of history remains unbroken. It suggests that if we ever discover a region of backwards flowing time, it would not be a lawless frontier. It would be a place of profound and inescapable order, where every action you take was always meant to be. The rigid determinism of a single, unchangeable past leads us to another breathtaking possibility. What if every choice you have ever made and every choice you did not make is equally real? This is the radical proposal of the many worlds interpretation of quantum mechanics. Developed by physicist Hugh Everett, it suggests that the universe does not settle on a single outcome. Instead, at every moment of quantum uncertainty, reality splits. Every possible result of every event blossoms into its own fully realized parallel universe. In this cosmic view, the timeline is not a solitary river but a vast, ever-branching delta with countless streams flowing simultaneously. Now place a temporal eddy within this infinite tapestry. If you were to enter a closed time-like curve and travel to what you perceive as the past, you might not actually be revisiting your own history. You could be crossing over into the history of a parallel branch, a universe almost identical to your own up until the moment you arrived. This single idea dissolves the grandfather paradox with elegant simplicity. If you were to prevent your own birth in that branched timeline, you would not be erasing yourself from existence. You would simply be creating a new universe where you never existed, while your original universe and the you who left it remains completely untouched. Your journey did not rewrite history, it just hopped to a different page in the infinite book of realities. In this framework, temporal eddies are more than just whirlpools in a single river. They become cosmic junctions, points where the flowing time of one universe loops back and connects with the flowing time of another. They are bridges across the multiverse. This interpretation offers a coherent, if staggering, vision of reality where backwards time flow and logical consistency can coexist. The river does not just flow backwards in some places, it constantly forks into new streams, and the eddies are where these streams momentarily touch. While most crystals are defined by their beautiful, repeating patterns in space, a time crystal is defined by a pattern that repeats in time. This is a new and bizarre phase of matter, one that was only confirmed to exist in laboratories within the last several years. Imagine a clock that ticks forever but never needs to be wound. It has no batteries, no external power source, yet its internal structure perpetually oscillates between two or more states. This is the essence of a time crystal. It is not creating energy from nothing, which would violate the laws of thermodynamics, but is instead in a kind of perfect, frictionless motion in its lowest energy state, known as the ground state. This breaks what physicists call time translation symmetry. In an ordinary system, if you perform an experiment today and then perform the exact same experiment tomorrow, the laws of physics will give you the same result. The system is symmetric in time, but a time crystal is different. Its properties change periodically with time, all on their own, meaning it looks different at different moments even with no external push. It has a built-in rhythm that the universe itself cannot reset. Now, this is not a machine for traveling to the past. You cannot ride a time crystal back to meet your ancestors. But it is a profound demonstration that time itself can have a structure, much like a diamond has a structure. It shows that in certain, finely tuned quantum systems, time does not just flow forward like a featureless river. It can pulse, it can beat, it can oscillate in a stable, repeating loop. This is a lower energy, laboratory-safe version of the kind of temporal weirdness we have been exploring. The immense whirlpools of closed time-like curves are like cosmic hurricanes in the river of time. Time crystals are like the persistent, stable ripples you might find in a sheltered pond, a small-scale hint of the same underlying principle, that time is not always a monotonous forward march. By studying these strange crystals, physicists are learning how complex temporal behavior can emerge naturally from the laws of quantum mechanics. They are a tangible, testable window into how time can be something more than a simple parameter in an equation. It can be an active, structured component of a physical system. If time itself can crystallize in a lab, what other temporal architectures might be possible out in the wild frontiers of the cosmos, near a singularity or woven into the fabric of a cosmic string? The existence of time crystals suggests that the river of time may not just have whirlpools and reverse currents, but also a hidden, intricate music, a rhythm that underpins everything. Even the most unbreakable law of physics might have a loophole. The second law of thermodynamics, which dictates that disorder must always increase, is the engine driving our one-way experience of time. But the law is fundamentally statistical. It is not an absolute command that every single atom must always become more disordered. Instead, it is a statement of overwhelming probability, a recognition that there are vastly more ways for a system to be messy than to be tidy. In a universe of infinite size and infinite time, even the most improbable events must occur somewhere, sometime. This includes the spontaneous formation of order from chaos. Imagine a box filled with gas, with all the molecules whizzing around in a state of maximum entropy. It is statistically possible, though incredibly unlikely, that every single molecule could suddenly, by pure random chance, gather into one tiny corner of the box, leaving a perfect vacuum everywhere else. From the perspective of that corner, entropy has just plummeted. The arrow of time, defined by rising disorder, has just reversed its local direction. For a fleeting instant, in that small pocket of reality, the thermodynamic river is flowing backwards. A shattered teacup on the floor could, in theory, spontaneously reassemble itself, its fragments leaping up from the ground to fuse back into a pristine whole. Heat could flow from a cold object to a hot one, seemingly defying everything we know. These are not violations of physics. They are statistical flukes permitted by the same mathematics that gives us the arrow in the first place. Of course, for any system large enough for us to notice, like a teacup or a person, the odds of such an event are so astronomically small that it is effectively impossible within the lifespan of our universe. You are far more likely to win every major lottery on Earth every single day for the next million years, yet the possibility remains etched into the laws of nature. This provides a profound and humbling thought. You do not need the warped spacetime of a black hole or a wormhole to find a temporal eddy. You could, in principle, find one in your own kitchen, if you are willing to wait for a duration longer than the current age of the cosmos. These thermodynamic whirlpools are the most democratic of temporal anomalies, arising not from cosmic violence or exotic matter, but from the quiet, relentless roll of probability itself. They hint that the forward march of time is not a fundamental dictate, but a powerful, persistent trend that could, in the most isolated and unlikely of circumstances, simply hiccup. The violent collisions of black holes send shudders through reality itself. These gravitational waves are not ripples in water or air, but literal distortions in the fabric of space-time, propagating outward at the speed of light. When two incredibly dense objects, like neutron stars or black holes, spiral into each other and merge, their immense acceleration warps the cosmos around them, generating these waves that stretch and squeeze everything in their path. We confirmed their existence directly in 2015, when the LIGO Observatory detected the faint chirp from a black hole merger over 1 billion light-years away. That signal was a perfect match for Einstein's predictions, a testament to the dynamic nature of gravity. But these detections only capture the clean, linear waves that have traveled across the universe. What happens in the heart of the chaos in the final frantic moments before the merger? This is the realm of non-linear, strong field gravity, where the equations of general relativity become fantastically complex. In this turbulent storm of spacetime, the distortions are so severe and so rapid that the fabric of reality might not just bend, it might tie itself into a knot. Could these intense, fleeting distortions momentarily twist the flow of time into a closed loop? The standard models we use to detect waves assume these effects are not present, but the full, untamed mathematics of Einstein's theory does not explicitly forbid it. A gravitational wave of unimaginable power, born from the most cataclysmic events in the universe, could potentially whip space-time into a transient whirlpool. For a fraction of a second, in a region smaller than an atom, the local arrow of time might spin backwards before the wave passes and reality snaps back to its normal rhythm. We would never notice such a microscopic, fleeting event from Earth, but its theoretical possibility is profound. It means that the universe's most violent explosions might not just be creating ripples in space, they might be seeding the cosmos with ephemeral temporal eddies, each one a flickering testament to the fluidity of time. As our gravitational wave observatories grow more sensitive, they are not just listening for new collisions, they are opening a new window into the most extreme geometries of space-time, searching for the hidden signatures of a river that, for just an instant, decided to flow uphill. Perhaps the most radical idea about time's nature comes from an unlikely source, the study of black hole information. When physicists calculated the maximum amount of information a region of space could possibly hold, they found a startling result. It is not proportional to the volume, as you might expect. Instead, the maximum information content is proportional to the surface area of the region's boundary. This is the holographic principle, a concept that turns our intuition about reality inside out. It suggests that everything happening within any volume of space, every star, every planet, every person, could be entirely encoded on a thin, two-dimensional surface surrounding it, like a cosmic hologram. Our rich, three-dimensional reality, with all its depth and solidity, might be a magnificent projection from a flat, information-rich screen. This idea forces a profound reevaluation of time itself. On that fundamental two-dimensional boundary, the equations describing reality might not include time as a primary ingredient at all. Time, in this view, would not be a fundamental river flowing through the cosmos. It would be an emergent phenomenon, a collective illusion that congeals from the complex interactions of countless bits of information. Much like the wetness of water emerges from the collective behavior of individual molecules, even though no single molecule is itself wet. If time is not a basic building block of the universe but a secondary property that arises, then its steady, forward flow is not guaranteed. It is a stable, large-scale effect, like the smooth surface of a lake. But just as a lake's surface can be broken by whirlpools and chaotic turbulence, the emergent property of time could become unstable. In regions where the holographic mapping between the boundary and our three-dimensional world becomes incredibly complex or breaks down, the illusion of linear time could shatter. The orderly progression of cause and effect might stutter, falter, or even reverse. In such a place, a temporal eddy would not be a whirlpool in the river of time. It would be a place where the river itself, the very concept of a flowing timeline, is momentarily failing to form correctly. This transforms our search for these anomalies. We are not looking for strange objects warping a fixed background of space and time. We are probing the limits of where space and time themselves emerge from a more fundamental and possibly timeless layer of information. The holographic principle suggests that the universe is writing its own story on a flat surface, and the flowing time we experience is just us, reading the words in sequence, one after another. But what happens if, somewhere in the cosmos, the story is being read backwards, or the pages are being shuffled by an unseen hand? If a black hole is a cosmic drain, then a white hole is its gushing fountain. This theoretical object is the exact time reversed opposite of its dark twin. Where a black hole's event horizon is a point of no return, a white hole's horizon would be a point of no entrance. Nothing from our universe could ever cross it to get inside. Instead, matter and energy would violently erupt from its core, spewing out into the cosmos without end. White holes are not just science fiction, they are mathematically valid solutions to Einstein's own field equations for general relativity. They are the other side of the coin, a perfect symmetric counterpart that the universe's laws do not forbid. Think of the river of time flowing relentlessly into a black hole, vanishing from our reality. Now picture that same river flowing outward from a white hole, gushing forth from a single point. One is a sink, the other is a source. The profound connection between them lies deep within the structure of an Einstein-Rosen bridge, a wormhole. In some interpretations, the interior of a black hole does not end in a crushing singularity. Instead, it transforms, connecting seamlessly to a white hole in a different region of spacetime, perhaps even in an entirely separate universe. This means a journey through a black hole might not be a one-way trip to destruction. It could be a tumultuous passage where the very direction of time, from the traveler's perspective, flips. You would fall inward, moving forward in your own time. But as you cross the bridge's midpoint and approach the white hole's exit, you would be violently expelled. To an outside observer in that new region, you would not be emerging from a black hole, but from a white one. You would appear as an effect without a visible cause, a person born from a singularity. Your personal timeline would remain continuous, but its direction would be reversed relative to the universe you now find yourself in. This is the ultimate temporal eddy, a cosmic structure where gravity so warps reality that entering a point of infinite collapse leads you to a point of infinite creation. While we have never witnessed a white hole, their potential existence completes a stunning picture of cosmic balance, suggesting that every drain in the river of time might have its corresponding spring. This logical knot, the grandfather paradox, is the ultimate challenge to our entire journey. Physics has a deep, almost instinctual need for consistency, a universe where events have clear causes and sensible effects. The mere possibility of a paradox, a logical contradiction baked into reality, is so unsettling that many physicists argue it is proof enough that backwards time travel is fundamentally impossible. The universe simply would not allow you to create a situation where you both exist and do not exist. It would be like a mathematical equation that claims 5 equals 3, a complete breakdown of reason. This need for causal order might be a physical law in itself, a rule woven into the cosmos that actively prevents the formation of any stable, macroscopic closed timelike curve. The river of time might be flexible, but perhaps it has unbreakable banks that stop it from ever looping back on itself in a way we could interact with. Yet the human mind is relentless in its search for loopholes. If the math allows for the bend in the river, how does reality avoid the paradox? One compelling answer is that it does not avoid it, it simply forbids it. Igor Novikov's self-consistency principle asserts that the past is an immutable fact. If you travel to the past, you were always there. Your actions are not new inventions, they are completions of a story that was already written. Your free will within the loop is an illusion, constrained by the absolute requirement that you do nothing to create a logical inconsistency. You might intend to change history, but some quantum fluctuation, a sudden gust of wind, or a simple slip of the hand would always intervene to ensure the timeline you remember remains intact. The universe, in this view, is a master editor, and it never allows a plot hole. Another breathtaking escape route is offered by the many worlds interpretation of quantum mechanics. In this radical vision, the paradox never happens because you never actually return to your own past. The moment you arrive in what looks like 1940, you have actually stepped into a parallel universe, one that branched off from your own at the moment of your arrival. In this new timeline, you can do anything you want, including preventing the marriage of your grandparents. You would simply be creating a new, separate universe where you were never born, while the original you from the original universe remains perfectly intact. The river does not loop, it forks, and your time machine is just a vessel that lets you hop from one stream to another. There is a third, more subtle possibility rooted in the quantum world itself. At the microscopic scale, the concepts of before and after are already fuzzy. Some physicists suggest that any attempt to create a macroscopic paradox would be thwarted by quantum effects run wild. The very act of a time traveler emerging from a wormhole might trigger a cascade of destructive quantum feedback, a surge of energy that instantly destroys the wormhole or alters the event in a way that preserves consistency. The universe might possess a kind of quantum immune system that attacks logical inconsistencies before they can ever manifest. So is the threat of paradox the final word, a definitive argument that shuts down the entire concept of temporal eddies? Or is it merely the puzzle that forces us to think more deeply about the true nature of cause and effect, and the astonishing ways the cosmos might enforce its own consistent story? The answer will determine if backwards flowing time is a physical reality or just a beautiful, forbidden idea. The hunt for a backwards flowing river of time begins not with grand machines, but with the subtlest of cosmic whispers. Detecting a temporal eddy directly is likely impossible with our current technology, but we can search for its ghostly fingerprints, the indirect evidence that causality is being broken somewhere in the cosmos. One of the most promising places to look is in the realm of high-energy particles. In vast underground laboratories or with detectors on mountain peaks, physicists observe cosmic rays, particles that rain down from space with immense energy. Within the chaotic spray of a particle collision, we might find a signature of reverse causation. Imagine tracing the path of a newly created particle backwards and finding its point of origin does not make sense. Perhaps a particle is detected an infinitesimal moment before the event that supposedly created it. This tiny, almost imperceptible violation of the expected sequence would be a seismic event in physics, a potential signal that the particle's history included a brief journey through a region where time flows in reverse. Our most powerful particle accelerators, like the Large Hadron Collider, are also on the front lines of this search. By smashing particles together at velocities approaching the speed of light, we recreate conditions not seen since the first moments of the Big Bang. In these fleeting, fireball-hot moments of creation, the very fabric of spacetime is stressed and twisted. It is within this primordial turbulence that microscopic temporal eddies could theoretically flicker in and out of existence. We would not see a tiny time machine, but we might detect an anomaly in the way energy and momentum are conserved in a collision, a statistical hiccup that points to an effect briefly preceding its cause. Another method looks to the stars, turning the entire universe into our laboratory. Quasars, the intensely bright cores of distant galaxies, and gamma-ray bursts, the most energetic explosions since the Big Bang, act as brilliant cosmic lighthouses. Their light travels for billions of years to reach us. If that light passed near a region of severely warped spacetime, a temporal eddy, it could carry a strange imprint. Physicists have speculated about the possibility of pre-echoes, faint copies of the main signal that arrive a split second before the primary flash. In a normal universe, this is nonsensical, like hearing an echo before you shout. But if the light is being bent not just through space but through a fold in time, such an anomaly becomes a theoretical possibility. We also have nature's most perfect timekeepers, pulsars. These spinning neutron stars emit beams of radiation with a regularity that rivals atomic clocks. By monitoring a network of these cosmic metronomes across the galaxy, scientists can create a supremely sensitive gravitational wave detector. A passing gravitational wave stretches and squeezes spacetime, minutely altering the rhythm of the pulsar's ticks. A temporal eddy would create a far more bizarre distortion. It could cause a temporary, localized scrambling of the timing signals, as if the steady flow of time in that region briefly stuttered or reversed. The data from all these searches has so far shown no conclusive proof. The river of time, from our perspective, appears resolutely uniform, yet the very absence of evidence is not a closed door. Every time an experiment fails to find a predicted particle or a new force, it forces us to refine our models. The ongoing, relentless quest to find physics beyond our current standard model and to test the limits of general relativity in extreme environments keeps the possibility alive. The first concrete evidence for a temporal eddy may not come from a dedicated search, but as a baffling, unexplainable anomaly in data from a future observatory, an event so strange that the only explanation left is that for a fleeting moment, we witnessed the river flowing backwards. The same mysterious force that is tearing the cosmos apart might also hold the key to its most twisted corners. Dark energy, the enigmatic driver of the universe's accelerating expansion, is not just pushing galaxies away from one another, it is actively shaping the geometry of reality. We do not know what dark energy is, only what it does. It possesses a strange negative pressure that counteracts gravity on the largest scales. This negative pressure is the engine of cosmic acceleration, but if its properties are not uniform, if the strength of dark energy fluctuates across the universe or evolves over deep time, then its influence could become far more complex and far more bizarre. In a region of space where dark energy density becomes exceptionally high, its repulsive push could grow so powerful that it does not just expand spacetime, it violently stretches it. Think of the fabric of the cosmos as an elastic sheet. Dark energy is the force pulling on all its edges. Now, imagine one small patch of that sheet where the pulling force is 1,000 times stronger. That patch would not just expand, it would thin and warp in ways that defy our smooth cosmic models. This intense, localized strain could potentially warp spacetime into a knot. The immense negative pressure might twist the fabric so severely that the paths through it, the world lines of particles, are forced to loop back on themselves. Under these exotic conditions, the formation of a closed timelike curve, a temporal eddy, moves from a theoretical curiosity to a plausible, if remote, consequence of dark energy's hidden behavior. This is not a gentle current in the river of time, but a violent whirlpool generated by the very force that is determining the universe's ultimate fate. The far future of the cosmos hinges entirely on dark energy's true nature. If it continues to accelerate expansion forever, we face a cold, lonely end as galaxies vanish over the cosmic horizon. In one particularly dramatic scenario, the Big Rip, dark energy's strength would grow without bound, eventually overcoming all other forces. It would tear apart galaxies, then solar systems, then planets, and finally the very atoms that constitute matter. In the final moments before such a cataclysm, as spacetime itself is being shredded, the conditions would be so extreme that the normal rules of causality might completely break down. The fabric of reality would be in a state of terminal turbulence, a chaotic storm where temporal eddies could flash into existence and vanish just as quickly. This suggests a profound and unsettling connection. The same force that is orchestrating the grand finale of the universe could also be creating fleeting pockets where time runs in reverse. Our search for these temporal anomalies is therefore woven into the greatest mystery in modern cosmology. By studying the acceleration of the universe, by mapping the distribution of galaxies and measuring the history of cosmic expansion, we are not just learning about our fate, we are indirectly probing the stability of time itself. Every new observation that constrains the properties of dark energy also tests the boundaries of where the river of time might not just flow forward, but curl back into a perfect and perhaps terrifying loop. This is the deepest challenge temporal eddies present, a question that reaches beyond physics into the core of who we are. Our entire concept of self is built upon a stable past, a personal history that defines our identity and our moral compass. Every choice you have made, every triumph and every regret has carved the person you are today. But what if those choices were not fixed in stone? The existence of regions where time flows backwards suggests that the past might be as malleable as the future, and this unravels the very thread of the self. If you could travel to a temporal eddy and undo a pivotal mistake, the person who returns would be fundamentally different from the person who left. Which version is the real you? The concept of a single, continuous identity shatters when your personal timeline is no longer a straight line, but a branching tree with roots that can be rewritten. This directly confronts our understanding of free will. If you can go back and change a decision, was that decision ever truly free, or was it merely a provisional step waiting for its own future revision? Our legal and ethical systems, our very sense of justice, are predicated on the unchangeable nature of the past. We hold people responsible for their actions precisely because those actions are permanent. But if actions can be undone, then responsibility becomes a fluid concept, as fleeting as a whirlpool in the river of time. The foundation of accountability crumbles. These questions have haunted philosophers for centuries, long before the mathematics of general relativity gave them physical form. One of the most famous frameworks is McTaggart's distinction between two series of time. The series views time as a flowing river of past, present, and future, a perspective that feels intuitive to our lived experience. The B series, in contrast, sees all events in time as equally real, simply strung along a permanent line of before and after relations. Temporal eddies deliver a devastating blow to the series. They suggest that the flowing now, the felt transition from future to past, is not a fundamental feature of the cosmos. Instead, they lend powerful support to the block universe view, an idea closely related to the B series and to the philosophy of eternalism. In this breathtaking model, the entire history of the universe, from the Big Bang to its final fate, exists all at once. Your birth, your life, and your death are all equally real and permanent parts of this four-dimensional block. What we perceive as the flow of time is just our consciousness moving along a single track through this vast, static structure, like a spotlight scanning across a grand movie reel. The past is not gone, and the future is not unborn. They are simply elsewhere in the block. This forces a radical re-evaluation of the relationship between time and consciousness. Is our awareness of a flowing present merely a biological trick, a cognitive illusion necessary for a finite brain to process a timeless reality? If the block universe is real, then free will in the traditional sense is an impossibility. Every choice you will ever make is already inscribed in the cosmic block, just as the final chapter of a book is already written. Your journey through life is not one of creation, but of discovery, uncovering a path that was always there. The existence of closed timelike curves would be the ultimate proof of this, creating literal, physical loops where every action is predetermined to ensure the consistency of the block. You would have the sensation of making a choice, but the outcome was fixed the moment the universe began. This is not a comfortable thought, but it is a coherent one. The possibility of backwards flowing time is far more than a puzzle about paradoxes and particles. It is a profound metaphysical challenge. It asks us to consider that our most intimate experience of reality, the steady drumbeat of seconds into minutes, into years, might be the grandest illusion of all. And if that is true, then what else about our place in the cosmos have we misunderstood? Our own cosmic cycle might be just one season in an eternal, repeating year. Some of the most profound cosmological models suggest the universe does not have a single beginning and a definitive end. Instead, it undergoes an endless, rhythmic dance of creation and destruction, a series of big bangs followed by either a cataclysmic big crunch or a gentle big bounce. In this breathtaking vision, the entire life of our universe, from its fiery birth to its final fate, is merely one turn of a wheel that has been spinning for eternity. And with each turn, something astonishing could happen to the flow of time itself. At the moment of maximum expansion, just as the universe begins to contract back in on itself, the cosmic arrow of time might not just slow down, it could reverse. From the perspective of a hypothetical observer outside the cycle, one cosmic era would see time flowing in one direction, and the very next era would see it flowing in the opposite direction. We, of course, are trapped within our own cycle, experiencing a perfectly consistent arrow of time where cause always precedes effect. But the larger architecture of reality would be a tapestry of alternating timelines, a cosmic metronome ticking back and forth through eternity. At the boundaries between these cycles, in the tumultuous moments of transition, the fabric of spacetime would be stretched and scrambled. It is in these liminal spaces between one universe and the next that colossal temporal eddies could form, whirlpools on a scale so vast they dwarf even the largest black holes. Two specific theories give this poetic idea mathematical form. The ekpyrotic model envisions our universe as a three-dimensional membrane or brain existing in a higher dimensional space. A cyclic universe in this model is driven by the collision of our brain with a neighboring one, a collision that appears to us as a big bang. In the aftermath, the brains move apart, the universe expands and cools, and then gravity slowly pulls them back together for another collision, restarting the cycle. At the point of collision and rebound, the fundamental laws might allow for a reset or even a reversal of the thermodynamic arrow of time. Another compelling idea is Roger Penrose's conformal cyclic cosmology. It proposes that as our universe expands forever into a cold, empty void, the vast scales of space and time lose all meaning. Distances become infinite yet relative, and the universe effectively forgets its own scale. In this strange state, the end of one eon becomes indistinguishable from the Big Bang of the next. The infinite future of one cycle smoothly connects to the infinite past of another. In this seamless transition, what happens to time? The conformal geometry that links the cycles could allow for a transformation where the local direction of time in one eon is inverted in the next, all while preserving the consistent experience of observers within each eon. This transforms our understanding of a temporal eddy. It is no longer a bizarre flaw in an otherwise linear cosmos. In a cyclic universe, backwards flowing time is an integral, predictable feature of the cosmic engine. The river of time does not merely have occasional whirlpools. Its entire course is a vast, looping spiral, winding through an endless sequence of universes. Our lives, our history, and our future are all part of one single, magnificent eddy in an infinite ocean of time. The smooth river of time we perceive may be a grand illusion. To find its true source, we must journey to the frontier where our two greatest theories of reality collide. General relativity paints a beautiful picture of a smooth, curving cosmos, while quantum mechanics reveals a fuzzy, probabilistic world. But when we try to combine them to describe the intense gravity of the Big Bang or the center of a black hole, the math breaks down into nonsense. This is the quest for a theory of quantum gravity. a single framework that can describe the universe at every scale, from the vastness of galaxies to the vanishingly small. And in this quest, our very understanding of time is being radically rewritten. Two leading candidates, string theory and loop quantum gravity, offer wildly different, yet equally mind-bending, visions for what time actually is. In string theory, our entire universe might be a three-dimensional membrane, or brain, floating within a higher dimensional space called the bulk. In this cosmic ocean, other brains could exist mere millimeters away, yet completely invisible to us. And on each of these brains, time itself could flow at a different rate, or even in a different direction. The temporal eddies we have been exploring would not be anomalies in a single river, but simply the natural currents of a neighboring brain occasionally brushing against our own. Loop quantum gravity proposes something even more fundamental. It suggests that spacetime is not smooth and continuous. Instead, it is woven from tiny, indivisible loops, a fabric of finite, grain-like threads. At the unimaginably small Planck scale, this granular structure becomes apparent, and our comfortable, flowing river of time simply evaporates. There is no smooth continuum for a river to flow through. Time, in this view, is not a background stage, but emerges from the changing relationships between these elementary loops, like the changing patterns in a vast cosmic tapestry. In such a reality, the ideas of before and after lose their absolute meaning. The sequence of events becomes a matter of perspective, dependent on your position within the quantum network. What we call a temporal eddy, a whirlpool where cause and effect reverse, would not be a strange distortion of a smooth fabric. It would be a natural, perhaps even common, feature of this more primitive relational structure. The river was never really a river at all, but the statistical average of a billion tiny, discrete events. Our search for the physics of temporal eddies leads us here, to the very edge of human knowledge, where time itself may be a temporary construct, a useful story we tell ourselves to make sense of a far more complex and interconnected reality. Your mind is the ultimate timekeeper, but its clock is built from memory and anticipation, not from fundamental physics. We feel time flowing forward because we remember the past and not the future, a psychological arrow that seems unbreakable. Yet this perception is a fragile construction of the brain, easily warped by extraordinary circumstances. A high fever can scramble your sense of duration, making seconds feel like hours. Certain forms of meditation can create a sensation of timelessness, where the flow of moments simply stops. A traumatic brain injury can even sever a person's connection to their own past, leaving them stranded in a perpetual, unfamiliar present. These disruptions prove that our internal timeline is a narrative we construct, not a direct readout of the cosmos. So what would happen if you stepped into a temporal eddy, a place where the physical arrow of time points backwards? Would your consciousness shatter, or would it simply flip its script? It is possible your brain would adapt, seamlessly rewiring your perception to maintain a coherent story. In this reversed flow, your memory would not be a record of what was, but a premonition of what will be. You would wake up remembering the entire day ahead of you with perfect clarity. Your morning coffee would be a familiar comfort you recall drinking in the future, and the conversation you are about to have would feel like a scene from a well-remembered story. Anticipation, that nervous looking forward, would transform into a strange form of dread or nostalgia for moments already experienced in your memory. You would live your life backwards from death to birth, yet your subjective experience would feel just as real and continuous as your life does now. The profound question is whether you would even notice the inversion, or if your mind would simply accept this new flow as the only reality it has ever known. This reveals a staggering possibility that the river of time we feel inside our heads is not a reflection of the cosmos, but a story we tell ourselves to make sense of our journey through it. The fundamental laws of physics insist that information can never be truly destroyed. This principle is a sacred rule in quantum mechanics, a concept known as unitarity. It means that the complete history of a particle, its properties and interactions, is never erased. It can be scrambled, spread out, and hidden beyond recognition, but it is never lost. This creates a monumental problem when we confront the ultimate cosmic shredder, a black hole. If you throw a book into a black hole, the book is obliterated, but what happens to the information contained within its pages? Does it vanish forever, violating this core quantum rule? This is the famous black hole information paradox. One stunning solution is the holographic principle, which suggests the information is not lost inside. Instead, it is perfectly preserved, encoded in a scrambled, two-dimensional form on the surface of the event horizon, like a cosmic fingerprint. Now, apply this same rigorous thinking to a temporal eddy, a whirlpool where time flows backwards. If you were to watch an event unfold within such a region from the outside, you would witness a breathtaking reversal. A shattered vase would spontaneously reassemble, leaping up from the floor to form a perfect hole on its table. From your linear perspective, it would appear as if information was being created from nothing. The precise configuration of every ceramic shard, the exact trajectory of each fragment, all that information seems to materialize out of the void to guide the reassembly. Conversely, if you watch the normal forward time version of the event first, the vase falling and breaking, and then saw it run in reverse, it would seem like all that intricate information was being utterly erased. Both perspectives from our outside point of view suggest a catastrophic violation of quantum law. Information cannot be created or destroyed, yet here it seems to be doing both. Therefore, any credible physical model for a temporal eddy must include a mechanism that preserves information consistency. The universe must have a way to keep the books balanced, even when the river of time flows uphill. This likely involves phenomena far stranger than simple reversal. One possibility is that the region of reversed time is not isolated. It could be quantum entangled with its surrounding environment, or even with a parallel universe in the multiverse. The information that appears to be created in the eddy is actually being borrowed or transferred from elsewhere, while the information that seems destroyed is merely being stored in a different part of the cosmic ledger. From a God's eye view of the entire multiverse, the total information remains constant and accounted for. The apparent creation and destruction is just an illusion, an artifact of our limited, linear perspective. Another, more profound idea is that within the eddy itself, the concepts of cause and effect are so deeply interwoven that the very question of information creation becomes meaningless. The reassembly of the vase and its initial shattering are a single, unified process, a closed loop where the effect is the cause and the cause is the effect. The information was always there, eternally cycling. The stringent demand that information be preserved acts as a brutal test for the physical plausibility of these temporal whirlpools. If a proposed model cannot explain how information consistency is maintained, it fails as a description of reality. This forces our theories to become more sophisticated, pushing us toward ideas like holography, quantum entanglement, and the multiverse. The behavior of information in these bizarre regions is not just a curious side effect. It is the ultimate arbiter of whether a backwards flowing river could ever be more than a beautiful dream. The power to navigate the river of time may one day rest in human hands. While our current technology cannot even conceive of building a temporal eddy, the theoretical pathways already exist. waiting for a future civilization with unimaginable energy and mastery over the cosmos. Consider the Alcubierre warp drive, a concept that does not propel a ship through space at impossible speeds, but instead manipulates the fabric of spacetime itself. It would contract the space directly in front of the vessel into a dense knot, while simultaneously expanding the space behind it into a vast, stretched plane. The ship itself would rest inside a stable bubble, a pocket of normal spacetime, surfing this engineered wave. In essence, the drive moves the universe around the ship, not the ship through the universe, cleverly sidestepping the light-speed barrier. Now imagine a far more advanced iteration of this technology. If you can contract and expand spacetime, could you also twist it? Could you take this malleable fabric and carefully knot a single thread of it into a perfect loop? This is the speculative leap from faster-than-light travel to a temporary time machine. Such a device would not be a grand tunnel like a wormhole, but a localized, manufactured whirlpool, a brief and controlled eddy in the river of time. The engineering requirements are beyond staggering. It would demand energy sources on the scale of entire stars and a flawless command over exotic matter to stabilize the violent spacetime curvatures and prevent the loop from instantly collapsing. Yet, and this is the crucial point, the known laws of physics do not explicitly slam the door shut on this possibility. The ethical weight of such a capability would be heavier than any black hole. Would we use it for historical research, to witness unrecorded moments with our own eyes? Would we attempt to correct catastrophic mistakes, meddling with the delicate chain of cause and effect that led to our present? The power to navigate time would be the ultimate human achievement, but it would also carry the ultimate responsibility. It forces a question far deeper than mere engineering. Should we ever take the wheel of a river that has flowed on its own since the dawn of creation? Deep within the violent hearts of spinning black holes, the universe might be hiding its most stable temporal eddies. A Kerr black hole formed from the collapse of a rotating star does not have a simple point like singularity at its core. Instead, its rotation smears the point of infinite density into a ring. This ring singularity is the gateway to the truly bizarre. The mathematics of general relativity suggest that passing through this ring does not lead to crushing oblivion, but into a region where the normal rules of space and time break down completely. Here, paths known as closed time-like curves are thought to weave through the geometry, offering a potential route where an astronaut could travel backwards in their own timeline. It is a cosmic carousel spinning at nearly the speed of light, where the past becomes a physical destination. Yet this theoretical wonderland is shielded by a destructive barrier called the inner event horizon, a region of infinite blue shift where any incoming radiation is amplified to unimaginable energy, likely vaporizing any object before it could ever reach the ring. This makes the interior of a rotating black hole both the most promising and the most perilous candidate for a natural time machine. Far from these gravitational monsters, another potential cradle for temporal eddies drifts in the vast voids between galaxies. Cosmic strings are hypothetical cracks in reality, thinner than a proton yet denser than a mountain range. If they exist, they could form into loops, and the spacetime inside such a loop would be profoundly twisted. The geometry is so warped that simply orbiting a cosmic string loop in a precise way could, in theory, send you back to a point in time before you began your journey. Unlike the chaotic interior of a black hole, a cosmic string loop offers a geometric and stable, though incredibly difficult to access, pathway to the past. You would not need exotic matter or immense energy, just the knowledge to navigate the contorted space around this primordial flaw in the cosmos. To find the true origin of temporal turbulence, we must look back to the very first moments of the universe. In the searing heat immediately following the Big Bang at the unfathomably small Planck scale, the fabric of spacetime was not smooth. It was a chaotic, boiling foam. In this quantum froth, tiny wormholes and tunnels could have spontaneously formed and vanished, and within these fleeting structures, the very ideas of before and after may have had no meaning. On this microscopic scale, temporal eddies were not anomalies, they were the norm. The steady, linear flow of time we experience today emerged only as the universe expanded and cooled, calming this primordial chaos into the recognizable cosmos we inhabit. The largest whirlpools in the river of time may have their origins in the smallest, most frantic moments of creation. Even the most violent events in the modern universe could be spawning ephemeral time loops. When two black holes spiral toward each other, their immense masses churn the spacetime around them into a storm of gravitational waves. In the final milliseconds before they merge, the curvature of spacetime becomes so extreme and dynamic that it might tie itself into a knot. For a fraction of an instant, in a region smaller than an atom, a closed timelike curve could flicker into existence. It would not be a stable gateway, but a transient whirlpool born from the most powerful collision since the Big Bang, vanishing almost as soon as it forms. At the center of every large galaxy lies a supermassive black hole, and in active galactic nuclei, these monsters are feasting. The intense radiation and powerful magnetic fields surrounding these entities create an environment of unimaginable energy. The spacetime here is not just curved by gravity, it is stressed and twisted by the sheer violence of the processes at work. In this cosmic maelstrom, the complex interactions between rotating spacetime, plasma, and radiation could, in theory, stabilize a temporal eddy or amplify a microscopic one from the quantum foam. These galactic cores are the universe's most energetic natural laboratories, where the conditions to twist time itself might occasionally be met. While we cannot visit these hostile realms, their existence proves that the universe is constantly experimenting with the very fabric of causality, creating and dissolving eddies in the great river of time. The final verdict on these cosmic whirlpools rests not in philosophy but in pure mathematics. Einstein's field equations, the very heart of general relativity, are a breathtakingly complex set of rules. They describe with perfect clarity how the presence of matter and energy warps the stage of spacetime, dictating how everything from a planet to a photon must move. These are not simple formulas you can scribble on a napkin. They are non-linear partial differential equations of immense power. Within their labyrinthine structure, specific solutions have been discovered that mathematically permit the river of time to loop back on itself. The Gödel metric, for instance, describes a universe that is rotating as a whole, a cosmos where every path eventually leads back to its own beginning. The Van Stockham solution models an infinitely long, rapidly spinning cylinder of dust, and its gravity is so intense that it twists spacetime into knots, creating closed paths through time. Even the interiors of certain charged and rotating black holes, described by the Kerr-Newman solution, contain these bizarre geometries where an astronaut could, in theory, follow a world line that circles back to an earlier moment. For mathematicians and physicists, these are not just abstract curiosities. They meticulously study the global structure of these hypothetical spacetimes, mapping their causal boundaries to understand where cause and effect break down. They analyze them for geodesic completeness, a technical term asking a simple question: can an object travel along any path in this universe without suddenly hitting a wall or falling into an infinite pit, a singularity where the equations themselves blow up and fail? The central, burning question is whether these mathematical curiosities could ever be more than that. Do they describe something that could actually exist in our universe? Many of these solutions require utterly unphysical conditions to survive, like an infinitely long cylinder or a perfect, smooth distribution of exotic matter with no lumps or imperfections. A single atom out of place could be enough to destroy the delicate balance, causing the entire temporal eddy to unravel in an instant. This is where the frontier of modern research lies, in the realm of numerical relativity. Scientists program Einstein's equations into the most powerful supercomputers on Earth, creating digital universes where they can test these ideas. They can simulate the formation of a potential time loop, and then introduce a tiny perturbation, a minuscule ripple in the spacetime fabric, to see if the structure is stable or if it collapses into chaos. The mathematics is the ultimate judge. It will tell us if backwards flowing time is a ghost in the machine of our theories, a beautiful mirage that vanishes upon closer inspection, or a real physical phenomenon waiting to be discovered in the untamed wilderness of the cosmos. The power to rewrite history carries a weight far heavier than any black hole. If we could step into a temporal eddy, the first question would not be how, but who. Who would hold the authority to make that choice? Granting any single person or nation the keys to time would be the ultimate consolidation of power. A dictator could simply erase their political opponents from existence before they were ever born. A corporation could travel back to patent every major invention, from the light bulb to the internet, creating a monopoly that controls all of human progress. The very concept of a fair and open future would vanish, replaced by a timeline meticulously curated for the benefit of a privileged few. The potential for abuse is so enormous it threatens the foundational idea of a shared human experience. Every decision to alter an event, no matter how well-intentioned, would ripple forward with consequences we cannot possibly predict. Preventing a single assassination might inadvertently trigger a global nuclear war. Saving a beloved historical figure could accidentally prevent the birth of the very person who would one day discover a cure for a plague. We would be playing chess with reality, but without knowing the rules of the game or ever seeing the whole board. This forces a deeply personal ethical dilemma onto each of us. If you had the chance to go back and fix your greatest mistake, the one that has haunted you for years, would you do it? That single moment of poor judgment, that one hurtful word spoken in anger, that opportunity you let slip away, each has shaped the person you are today. Our regrets and our triumphs are woven together into the fabric of our identity. To remove a single thread, to undo a foundational failure, might unravel the entire tapestry. The person who returned from that journey would not be you, not the you who learned from that pain and grew stronger for it. Our fallibility is not a flaw to be corrected. It is the essence of our humanity. These are not just thought experiments for philosophers or plot devices for science fiction. If the physics of temporal eddies is real, then these questions become urgent matters of global security and existential risk. Establishing a framework for the ethical use of such a power would be the greatest challenge humanity has ever faced. It would require a level of international cooperation and profound wisdom we have never yet achieved. A universal treaty forged not for peace among nations, but for the protection of time itself. Our journey through the physics of temporal eddies has taken us from the solid ground of our daily experience to the very edge of what is theoretically possible. We have followed the river of time from its familiar, forward-flowing banks into the heart of its most bizarre and twisting whirlpools. Einstein's relativity showed us that spacetime is a flexible fabric, capable of being warped into loops where the past and future connect. Quantum mechanics whispered that at its foundation, time might be a symmetrical thing, indifferent to the direction we hold so dear. We explored cosmic structures like wormholes and black holes, envisioning them as potential gateways and natural laboratories where the arrow of time could, under the most extreme conditions, reverse its course. The mathematics does not forbid these possibilities, it invites them. Yet for all this theoretical wonder, we must stand on the sobering shore of observation. No experiment, no telescope, no particle detector has yet found a single, concrete piece of evidence that a temporal eddy exists. The river, from our limited vantage point, appears to flow in one unyielding direction. But the profound value of this exploration is not in proving these ideas are real, but in proving that they are possible within the logic of our universe. This mathematical consistency forces us to think bigger, to expand our imagination beyond the comfortable confines of a linear timeline. The true river of time may be a thing of immense complexity, with hidden currents, deep whirlpools, and counterflows that we simply cannot perceive from our tiny raft. Perhaps the greatest lesson this journey imparts is one of deep humility. Our perception of reality, as vivid and certain as it feels, is limited by the very laws that govern our brains and our instruments. We are built to experience one narrow slice of a cosmos that may be infinitely more strange and interconnected. The universe holds mysteries that lie beyond our current comprehension, realms where causality is fluid and the past is not a fixed monument, but a living part of the whole. The search for understanding does not end here, it is amplified. It is driven by that timeless human desire to look past the horizon of the known and ask the next great question, to seek the true, magnificent nature of our existence. What do you think lies in the deeper currents of time? Share your own mind-bending thoughts in the comments below, and if you want to continue exploring the cosmos' greatest mysteries with us, be sure to subscribe.